Yeah, hello everyone. So this is a question from JEE Mains 2026 28 Jan evening. The number of isoelectronic species among scandium plus 3, chromium plus 2, manganese plus 3, cobalt plus 3 and iron plus 3 is n. If n moles of AgCl is it's formed during the reaction of complex with formula COCl3 En twice NH3 with excess of AgNO3 solution, then the number of electrons present in the T2G orbital of the complex is okay. So this involves the chapter coordination compounds, and so we'll first go step by step. Isoelectronic species. So the meaning of isoelectronic is those guys having the same number of electrons. Okay, so we'll write it down. Isoelectronics are species having same number of electrons. Okay, so they are saying the number of isoelectronic species among, so they have given us a list and we have to find out how many of them are isoelectronic. Okay, so we know that scandium atomic number is 21, so 3 plus will have how many electrons? 18 electrons. Then we have chromium plus 2. We know the atomic number of chromium is 24, so plus 2 will contain 22 electrons. Then we have manganese plus 3. Atomic number of manganese is 25, so it will contain 22 electrons. Then we have cobalt plus 3. Atomic number of cobalt is 27, so therefore cobalt plus 3 will contain 24 electrons. Next we have iron plus 3. Atomic number of iron is 26, so plus 3 will contain 23 electrons, right? Okay, so in the question they are saying number of isoelectronic species among them is n. Okay, so when we observe them carefully, we see that Cr plus 2 and Mn plus 2 are the isoelectronic species, so n is equal to 2. So 2 of them are isoelectronic, so therefore n is equal to 2. Okay, so next step, if n moles of AgCl is formed during the reaction of complex with formula COCl3 En twice NH3 with excess of AgNO3. Okay, so let us write that down, that when we react the complex, this is the second part of the question, complex COCl3 En twice NH3 plus excess of AgNO3, we get 2 moles of AgCl. Okay, so this information is very important to us because this will help us to find out the formula of the complex. From this, we don't know what is outside the coordination sphere, how many atoms are inside it, what is the coordination number. So therefore we cannot calculate anything about the oxidation state of the central metal atom without knowing the formula, right? So this is one information which is given to us, that this complex, whenever it reacts with excess of AgNO3, we get 2 moles of AgCl. So from this information, since AgNO3 is reacting with this complex, right, and we are getting 2 moles of AgCl, that means there must be 2 Cl atoms outside the coordination sphere. From this information, 2 Cl atoms per molecule must be outside the coordination sphere. Okay, so I will explain why. So that means the formula of the complex will be CO En twice NH3Cl and 2Cl outside. Okay, so this is the actual formula of the complex. So this complex, whenever it reacts with excess of AgNO3, so we get 2 moles of AgCl. Okay, So now to understand why two are outside, because it's a very important thing that species which are present, I mean the atoms which are inside the entity, the coordination entity, okay, this won't dissociate. Okay, so that means these guys whatever are present inside, they won't dissociate. So therefore this chlorine is linked to this central metal atom by coordination bond, it is not going to dissociate, right? So therefore the chlorine which is present outside the coordination entity, that chlorine can react with the excess AgNO3. And since we are getting 2 moles of AgCl, that means there is, you know, so we are getting those 2 moles because Cl2 is outside. Total Cl is 3. So therefore 2 must be outside. That's why we are getting 2 moles of AgCl. Okay. So therefore this is the formula of the complex. Okay. And if we observe it carefully, it's a heteroleptic complex because it contains different kinds of ligands. Okay, so one of the ligand is ethylene diamine, one is, you know, ammonia, the other one is chlorido. Okay, now some information about ethylene diamine, that is En, is ethylene diamine, and its formula is NH2 CH2 CH2 NH2. Okay, so it is a didentate ligand. Okay, so that is one molecule can donate or form 2 coordination bonds simultaneously at the same time. So therefore it's a didentate ligand. So what will be the coordination number of this complex? 2 per ethylene diamine. So there will be 4, 5 and 6. So there are total 6 coordination bonds. So therefore the coordination number is 6. Okay, so our next step is to calculate. So we'll write down the complex CO, coordination number is 6. COEN, 2 NH3 Cl and Cl2 outside. Okay, so our next step is to calculate the oxidation state of cobalt. Okay, for that we need to know the charge of the complex ion, right? So the charge of 2Cl is -2. So therefore we know, right, coordination compounds are neutral. So therefore the charge of this complex ion must be +2. Okay, so the charge of this is +2. Okay, now assume the oxidation state of cobalt as X. Okay, so X plus the En is, you know, does not contain any charge. Ammonia also does not contain any charge, but chlorine is a ligand which has a charge of -1. So there is one atom of chlorine. So therefore X plus -1 will be equal to +2. So therefore X is equal to +3. So the oxidation number of cobalt in this particular complex is +3. Okay, cool. So now we need to know the configuration of chlorine. So chlorine in ground state is 3d7 4s2. So why are we doing this? Because in the question, if we go and check in the question, they are asking us that n moles of AgCl is formed during the reaction of complex, correct? Number of electrons present in the T2g orbital of the complexes. So we need to know the configuration. Okay, we have to know the electronic configuration of the central metal atom. Okay, so we know that, okay, it exists in a +3 oxidation state. So in the ground state, cobalt's configuration is 3d7 4s2. So therefore the configuration of +3 will be remove 2 electrons from the outermost shell, then 1 from 3d, so we'll be left with 3d6. Okay, now whenever the configuration is 3d6, there are 2 states possible. Okay, so what do I mean by 2 states? So obviously we know, right, that in coordination compounds, the 5 degenerate d orbitals, they are not degenerate anymore. They split into 2, that is Eg and T2g, right? 2 above and 3 below. They split into the degenerate or d orbital split into Eg and T2g. right? So based upon that, there are two states possible. That is, one of the state is, so let us draw EG and T2G. This is, let's say this is case 1, and let's draw one more set of them. Let's say this is state 2. Okay, so sorry, case 2. So what can happen is, that, okay, so we need to have 6 electrons, right? So what can happen is, okay, 1 2 3, then the fourth one goes to EG 5, and then pairing starts. This is one possibility, when this the splitting, that is the difference between EG and T2G is small, when this difference, that is delta, is small. The second case is, when the difference, that is when the splitting of these, the energy, crystal field splitting energy is, large, when delta is large. So then what's going to happen, electrons, obviously they will first fill the T2G, and instead of going to the EG, because they will find it difficult now to go to the EG because the energy is high. So therefore they will start pairing up, right? So this is the two states possible. If we have state 1, then it will result into, as you can see, it will result into high spin, because this contributes +1/2 +1/2 +1/2 +1/2 to the total spin, and this contributes 0. So the spin here will be high, so therefore this is known as high spin. And high spin will be caused by a weak field ligand. Because why by weak field ligand? Because the delta is small here, crystal field splitting is small, so therefore it must be a weak field ligand. Okay, in this case 2, you can see the total spin is 0, because we have electrons of opposite spins in every orbital, so therefore this is a low spin complex, and this is produced by strong field ligands, because in this case the crystal field splitting energy is large, and that must be produced by a strong field ligand. Okay, now to decide which spin state is going to happen in this case, so we have, so to decide if the, and this is a heteroleptic complex, so to decide if heteroleptic octahedral complex is high or low spin, we have certain conditions. So there are two conditions or two criterias. So the first one is the ligand strength. Okay, so if majority of the ligands are strong field ligand, then the low spin condition will be favored, as because they will produce a high crystal field splitting, so that will be very high, and hence therefore they will pair up, producing low spin. Okay, if majority of the ligands in so we'll write it down, majority of ligands are strong field, then low spin favored. As delta large, so therefore they can pair up. Okay, so to understand, I will draw the two sets of EG and T2G. So if the majority of the ligands are strong field ligand, so that means they will produce a high delta value, that is crystal field splitting energy will be very high. So therefore electrons will find it difficult. So after filling 3 electrons, the fourth one will find it difficult to go to EG. Instead they start pairing up. So after the third one they start pairing up. And because of that pairing up, you can see the spins are getting cancelled. So therefore it will result in a low spin complex. Okay, this is the first condition. Second one, so in our case, in our complex, you can see we have 3 ligands. Ethylene diamine is quite strong, ammonia is also strong, chlorine is, it's on the weaker side. So therefore majority of the ligands are strong field ligand. Okay, so therefore case 2 will be preferred. Okay, what is the second criteria? Second criteria is it depends upon the oxidation state of metal. Okay, so high oxidation state, that is +3 or more, favor low spin. Okay, so what might be the reason? Whenever we have higher metal oxidation state, since the oxidation state, or the positive charge on the metal is very high, it increases the electrostatic attraction with ligands. Okay, so for example, when in this case we have +3 oxidation state, so cobalt +3 is highly, or you can say it is positively charged, so the ligands are going to interact a lot. The ligands, so in this case I'm representing the ligands like this. So these guys are going to interact with CO+3 a lot more. Okay, and because of that they will produce a strong ligand field because of the interaction, because they will come very close near to the central metal atom. Because of the higher electrostatic interaction, they will cause a very high ligand field. And also one more thing is, the coordination number is 6 here, so therefore there are 6 ligands, 1 2 3 4 5 6 of them, and they are going to interact with 5 d orbitals of the central metal atom, right? 6 ligands interacting with 5 d orbitals, so therefore there will be high repulsions. Okay, and because of these high repulsions, it causes the splitting of d orbitals further. Because of these repulsions, the splitting will be higher. Okay, so therefore the gap, that is crystal field splitting energy between them, will be high. So therefore they will start, so after the third electron, instead of going to Eg, this doesn't happen. So what they do is they start pairing up, because this energy is very high, so they won't be able to go to the Eg. So therefore, following the second point also, our complex is going to be a low spin complex. Okay, so this is the configuration that it is going to follow. Okay, this is the spin state that it is going to take. Case 2 is the spin state that it is going to take. Now in the question they are asking us how many electrons are there in the T2G state. So you can clearly see above one is Eg, below one is T2G. How many electrons are there in T2G? 2 3 4 5 6. So therefore the answer will be 6.